Imagine an ocean larger than all of Earth's oceans combined, hidden beneath a shell of ice, in complete darkness, warmed by the heat of a planet's gravitational grip, and possibly teeming with life. Now imagine that ocean is not on Earth. It's on a moon of Jupiter, 390 million miles away. And we have already found evidence that its water is reaching the surface, venting into space, waiting to be sampled. That moon is Europa, and it may be the most promising address for life in the entire solar system. When the Voyager spacecraft flew past Jupiter in 1979, the images it sent back of Europa were puzzling. The moon's surface was almost perfectly smooth, smoother than any other solid body in the solar system, and it was covered in a network of reddish-brown lines crisscrossing the white ice like cracks in a hard-boiled egg. Scientists quickly realized what they were looking at: a thick shell of ice, fractured and refrozen, floating on top of a liquid ocean below. The lines were places where the ice had cracked, shifted, and refrozen, stained by minerals welling up from the ocean beneath. The evidence for that ocean has only grown stronger in the decades since. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, measured Europa's magnetic field and found that it was being disrupted in a way that could only be explained by a layer of electrically conductive liquid beneath the surface, almost certainly salt water. More recent observations have detected water vapor plumes erupting from Europa's surface, similar to the geysers of Yellowstone but on a planetary scale. Water from the ocean below, venting into space through cracks in the ice. These plumes are a remarkable gift to scientists. They mean that material from Europa's hidden ocean is being delivered directly to space, where a passing spacecraft could sample it without ever having to drill through the ice. And that ocean is not small. Scientists estimate it contains about twice as much liquid water as all of Earth's oceans combined. It has been liquid for billions of years, kept from freezing by the tidal heating caused by Jupiter's immense gravitational pull, the same force that flexes and heats Europa's interior as it orbits the giant planet. This tidal flexing generates heat in Europa's rocky interior, keeping the ocean liquid even though Europa is far from the sun. And at the bottom of that ocean, where the water meets the rocky sea floor, there may be hydrothermal vents, the same kind of geological features that support thriving ecosystems in Earth's deep ocean. If Europa has hydrothermal vents, it has everything we know life needs: liquid water, chemical energy, and a diverse array of elements. The case for life on Europa is not speculative. It is grounded in solid science, and NASA is taking it seriously enough to have launched the Europa Clipper mission, which is currently en route to Jupiter and will arrive in 2030. The Clipper will make dozens of close flybys of Europa, studying its ice shell, its ocean, and its plumes in unprecedented detail. It will measure the thickness of the ice, the composition of the plumes, the chemistry of the surface, and the magnetic field of the ocean. It won't land on the surface or drill through the ice, that's a future mission. But it will tell us far more than we currently know about whether Europa's ocean could support life. Now, let's travel a little further out in the solar system, to Saturn, and to a moon that in some ways is even more exciting than Europa. That moon is Enceladus, a small, icy world only about 500 kilometers in diameter that has become one of the most talked about objects in astrobiology. Small it may be, but what it is doing is extraordinary. In 2005, the Cassini spacecraft made a discovery that stunned the scientific world. It found that Enceladus was actively venting enormous plumes of water vapor and ice particles from its south pole, geysers erupting from cracks in the ice called tiger stripes. The plumes were shooting material hundreds of kilometers into space, and some of it was escaping Enceladus's gravity entirely and feeding Saturn's E-ring. The entire ring, one of Saturn's most prominent features, is being continuously replenished by the geysers of this tiny moon. Cassini flew through those plumes and analyzed their composition. What it found was extraordinary. The plumes contained not just water, but organic molecules, complex carbon-based compounds. They contained hydrogen gas, which is produced by the reaction of hot water with rock, a process called serpentinization, which also occurs at hydrothermal vents on Earth. They contained silica particles that could only have formed at temperatures above 90 degrees Celsius, indicating active hydrothermal venting on the ocean floor. They contained molecular hydrogen in quantities that suggested ongoing chemical reactions between the water and the rocky sea floor. And they contained carbon dioxide, methane, and ammonia, all molecules relevant to the chemistry of life. In other words, Enceladus has a warm, chemically active ocean with hydrothermal vents, organic molecules, and all the ingredients that life needs. And it is actively sending samples of that ocean into space, where a spacecraft can fly through and analyze them without even having to land. This is almost too good to be true. Enceladus is, in the words of one NASA scientist, the most habitable place we know of beyond Earth. And the fact that it is actively venting its ocean into space means that a future mission could potentially detect biosignatures, chemical signatures of life, without ever having to drill through the ice. A mission to do exactly that, a dedicated Enceladus life finder, has been proposed and studied. It hasn't been approved yet, but the scientific case for it is compelling. If we want to know whether life exists beyond Earth, Enceladus may be the place to look first. The cost and complexity of such a mission would be significant, but the potential payoff, the definitive detection of life beyond Earth, would justify every penny. The discovery of these ocean worlds, Europa, Enceladus, and others like Titan and Ganymede, has transformed our understanding of where life might exist in the solar system. We used to think the habitable zone was a narrow band around a star where temperatures allowed liquid water on a planet's surface. Now we know that liquid water can exist far beyond that zone, hidden beneath ice, warmed by tidal forces. The habitable zone is not a ring around a star. It is a volume of space that includes every world with the right combination of liquid water, chemistry, and energy. And that volume is far larger than we thought. Our solar system alone may contain multiple habitable worlds, and we are only beginning to explore them. Subscribe if you want to keep following this journey, because in the next episode, we're going to leave our solar system entirely and look at the thousands of worlds orbiting other stars, asking which of them might be home to something living. We're heading to other star systems next, thousands of worlds, and some of them look remarkably like home. Subscribe and keep watching. The best is yet to come.